Hey programmers, Alvin here. Right now I want to walk through the JavaScript solution for this tree sum problem. And I think this time around I'll jump right into the recursive version, right? So we'll start recursively and we'll begin with our base case, right? My base case is always about the simplest version of the input where I just know the answer without needing any additional calculations, right? I know that the simplest tree here that I could be given is going to be the empty tree, right? If I have the empty tree, that means my root is null. And if your root is null when you have the empty tree, what is the sum of the empty tree? Well, kind of inherently, it's just 0. So that'll be my base case. Nice. And then from there, I'll think about how I can compute my answer given my children results. So I need to find the result of the sum of my left subtree and also the sum of my right subtree. So just call recursively. So tree sum of root left as well as tree sum of root right. Cool. And I know that these two calls, they return numbers, right? Representing the sum of my left subtree and the sum of my right subtree. As the parent, that is as the root, how can I find my total sum? Well, it just is myself, so root.value, plus everything in my left subtree, plus everything in my right subtree, right? And we'll go ahead and just test this out the gate. But this is nothing fancy, a really elegant code. So if you look at the test cases here, we do have some diverse outputs. So this code does work on trees of all different shapes and sizes. Something that helps me, really believe the magic of recursion is to just analyze the assumptions here, right? So let's say that I'm stepping through tree sum and my root is this 3 over here, right? So I check the base case. Is this 3 node null? It's not, so I must make the recursive call, right? And I know that when I break down this code recursively, I know what root.val is going to be like 3, so I'm kind of corresponding this comment with the thing below, right? And then when I make the recursive call on tree sum root.left, that means I'm asking for the total sum of this subtree starting at 11. So I'm looking at the 11, 4, -2 subtree, right? If I take the total sum of just that left subtree, it looks like it's going to be just 13. So now I'm saying plus 13 over here, right? If I do the same thing on the right subtree, I know that this call is for this 4 node, right, and all of its children. That should just magically return, by the power of recursion, that should return 5, right? I'm going to assume that that recursive call just works. So here I have the 5, right? If I take the total sum of these, 3 plus 13, 16, 16 plus 5 is 21, that would give me the correct answer, right? So to have some confidence in my recursive code, I just write the code and then I assume correctness from my recursive calls, then I figure out how I can take those sub-values from my children, combine it with my own value, and that should be my final answer. So here is the recursive version of this solution, which would be some sort of a depth-first traversal technically because it's recursive. And if you'd like, I can also show you the iterative version. So let's just do that. And I always practice usually my problems doing both the recursive as well as iterative version if it's reasonable, and it is really reasonable here. Hopefully you're familiar with our breadth first code by now, right? So I'm just going to start by checking, hey, if you're given some root that is already null, then that's kind of just an edge case. I'll just go ahead and return 0, right? Because the sum of that empty subtree, or that empty tree rather, is just 0. Then I can begin my main code. So while my queue is not empty, so I'll start with a queue who begins with the root, and I want to loop while my queue is not empty, so while queue.length is bigger than 0. I'll begin a single iteration of my while loop by just shifting out the front of my queue. So in JavaScript, for me, that's queue.shift. That removes the front element and also returns it to me, so I'll save it in current. And then from there, now that I have this current, I know that that contains the value that I actually care about. So what I would do is go ahead and track some running sum. So I'll say let sum, or maybe I'll say let total sum equals 0. And as I remove something from the front of the queue, I'll take its value and add it to my total sum. So that will accumulate all of the values, right, into a sum. Then from there, I just need to add my classic logic of checking for my children, right, if they exist. So if I have a left, so if current.left is not equal to null, then what I'll do is add that left child into my queue. So queue.push my current.left. Again, make sure you're following your queue rules, right? So shift removes from the front, push adds to the back. It's really important that my shift and my push, or my add and remove methods, work on opposite sides of my queue. Otherwise, it's not a queue, right? So that looks good to go. And I'll write something symmetric for the right-hand side over here. And by the end of my function, I'll just go ahead and return my total sum. Nice. So this would be my go-to iterative version. Of course, it's technically a breadth first, and we'll give that a test. Nice. And here we have that solution. So one thing to note, I think it's pretty important to be consistent in how you implement these algorithms, at least where possible. So you'll notice that I always am a fan of writing my processing logic for a node. Here I consider the processing logic where I add the value of my current node into my total sum. I do that processing logic typically when a node leaves the queue and not when the node is added to the queue. And it just ends up being less repetitive that way. For example, I've seen some people write code like this where it's like, all right, well, I guess since I'm adding my left child into my queue, that means it exists. So not only will I push it, but I'll add it. So I'll do, I don't know, total sum plus equals current dot left dot val, right? So I'm kind of adding the child's value as soon as it's added to the queue. And you can write something symmetric for the right-hand side. And you can see that because of this, I kind of have to double up all of my code, which does not make it super clean. And I think something that is even worse than that is, well, now you actually never added your root value into your total sum. So you would have to begin your total sum as root.val. And at this point, I'm like, I kind of just hate this code, right? So you can run this. This would probably work. So this code totally works, but it's not what I think is the best design for this pattern. So I'd rather write it like this, right? Consume your values when they leave your queue, because eventually everything's going to leave, right? So I'll prefer it at least like this. Cool. So before you go on to the next problem, I recommend you practice both versions of this problem. So do it recursively, do it iteratively, have them both down pat, because we're going to increase the difficulty right now.